Okay, so our next speaker is also our alumni and Dr. Raghav Sharma. Presently, he is working at the National University of Singapore since 2018 as a postdoc and in the group of Professor Yan Yang. He's currently working on various spintronic and other electronic devices for specifically for energy harvesting applications, using both spintronic and topological materials for software error signal detection and generation, spin orbiter waste efficient switching, and so on. So he did PhD from our group at IIT Delhi and in the year 2017, and where he was working on tunnel junctions primarily. Okay, Raghav, I think with that you can start your talk. Are you able to share your screen?
Yeah. Is it visible?
Yes, but
Your
you
voice
speaking?
has some problems.
We cannot hear you.
Now it's okay.
It's a bit low.
Okay.
I cannot hear at all.
For me, it's low.
Now it's fine.
No improvements.
Hello.
Maybe you can remove your headset and try to use the mic of your laptop if you are using a laptop.
So now it's fine.
A bit better.
Oh, okay. So sorry for this interruption. So can I start if I am audible?
Yeah, you have to speak little close to the mic
Okay, I will try my best. So
and maybe little loud also.
okay, okay.
Okay, you can start now.
Okay. So first of all, thank you very much to Professor Mudli. First of all, I would like to congratulate Professor Mudli and the other team members of Spin Dynamics at IIT Delhi for 10 years. Being the first PhD student, and also I'm completing 10 years in the field of spin. So today I am very happy to present my work, basically my progress in the field of spintronics in last 10 years. So right now I'm working at as a postdoc at National University of Singapore under Professor Yang, and I'm mainly working on development of high frequency rectifiers and also oscillators using spin torque, and also I'm working on some topological materials using this nonlinear Hall effect for the applications such as energy harvesting. So the motivation behind this work is the wireless energy harvesting. So our environment is full of, many signals wirelessly like GSM, 3G, 4G, 5G, and the most popular one is actually 2.45 gigahertz, which is coming from our Wi-Fi routers also. So this energy harvester, can convert the wireless energy into some useful DC power. And this is actually very useful for many applications. And one of the applications is actually like you have sensors and you have to put that sensor in the remote area where you don't want to replace the battery. So these energy harvesting chips actually can be integrated with your sensors, and that can automatically charge your sensors by the wireless energy. So coming to my work, so I'm mainly working on the diodes, making rectifiers using some spintronics or some alternative materials. So typically diode is basically conduct in one direction. So if we have alternative signal applied to this diode, so we have some DC voltage, one direction only. So that is typical diode and rectifier. And commercial available is the Schottky RF detectors, and they show typically like 500 to 1000 millivolt per milliwatt, that is sensitivity of these Schottky diodes. And also, if you apply a bias to these Schottky diodes, they can go up to 4000 5000 millivolt per milliwatt. But I'm proposing the alternative, which is spintronic rectifier, like this kind of MTJ based spin diodes or spin oscillators. So the advantage of using this in these kind of energy harvesting systems, so they will be used as a rectifier, and the advantage is actually this wide frequency tuning, which is not present in these Schottky diodes, and then high sensitivity. So if recent papers where they showed with this tilted anisotropy in the free layer, they have shown a very high zero bias and with bias sensitivity of these spin diodes. And also recent reports propose that they can work at low power, which Schottky diode cannot. So the basic principle of this MTJ based spin diode, so basically you have this fixed layer, you have this insulator and free layer. Typically this free layer is tilted. So when you apply this AC signal, so when the AC signal is positive, your precession angle will be more, and you will have high resistance. And similarly, when the signal is negative, your precession angle will be less, and you will have kind of negative fluctuation in the resistance. So resistance will be less. So the voltage is developed in these devices because of this multiplication of I into delta R, and which will be like your DC voltage. And this is the typical signal, which is because of your spin transfer torque, or either from the effective field, which the magnetic field you have applied. So we have basically this Lorentzian plus anti-Lorentzian kind of, rectified signals. So coming to some spin diode literature reviews. So recently, people have shown that these spin diodes can have high sensitivity and high maybe rectified voltage. Than the Schottky diodes. But for that, actually, they use this tilted kind of anisotropy, which is very useful for the high sensitivity, because you can actually excite a very high precession angle, and also very good for this field-free rectification. And also by this equation, actually, if we add the DC bias, so you can increase the sensitivity as well as the rectification voltage of these devices. So now coming to our work, so we use these kind of devices for the energy harvesting setup, and before doing that, actually we tested our samples. So typically one spin diode is not very useful for the energy harvesting. So that's why we connected 4 oscillator, or you can say diode also, in parallel and series. So for testing whether which kind of configuration is useful for the energy harvesting. So we use this tilted kind of STOs with this much high TMR of 80%, and we connected this oscillators or diodes by bonding on this kind of chips, where we applied and the RF, and we measured the DC voltage using these connectors. So for the zero DC bias, since they are having canted anisotropy, they when we connected 4 diodes or oscillators, they show a very broadband kind of signal. And as we increase number of oscillators in this series or parallel connection, they show a increase in the DC rectified voltage. And similarly, when we apply DC bias, so when we apply DC bias, there is a spin torque, and that also increases your DC voltage. So we reported actually up to like 100 millivolt from using these 4 devices in series. So now we can see that series configuration, which is shown by this orange curve, so it's more useful, and you can easily think that even the batteries and solar panels actually we connect in series, because these spin diodes act as a voltage source, and when we connect in series, their voltage will increase. So after this initial testing, we have connected 8 oscillators in series. So this signal generator used as a source, and this is a patch antenna which can generate at a signal at 2.45 gigahertz. So we bombarded the chip with the 2.45 gigahertz signal at 0 dBm, and we observed 30 millivolt. At the output of this oscillator chip. So we connected this. We stored this voltage into this supercapacitor, and by using this booster, we converted this 30 millivolt to some like 4 volt. And from 4 volt, we have lighting up this LED. So this is basically the demonstration of energy harvesting system using this STO arrays. Also, we have shown that this kind of setup is capable of holding the voltage for 1 minute at least. So since your Wi-Fi routers are not continuous, so that is also very useful for the actual applications. Further, since the last experiment was at 0 dBm, so we further optimize our devices for the low power operations, and we find that we compare this with one of the best Schottky diode, which is HMS. So these devices can show even 80% the efficiency, but the problem is they can only work above 0 dBm, as you can see by this red curve. And these spin diodes are actually can work at low power only, but high power actually they show a very low efficiency. So basically, there is a optimization at high power. At high power, you can use this Schottky diodes, but at low power, actually, these STOS arrays are more useful. And now, if you know the power from the Wi-Fi router, which is coming to our mobiles, is typically -30 to -67 dBm, where this Schottky diode cannot work. So that's why these STOS arrays are very important for anything below this -25 dBm. And further, after this low power detection, also they can show some kind of broadband rectification. So in one of the recent work, when you have certain tilted angle in the free layer, so you can excite a very high kind of precision angle from in plane to out of plane, and that can show this kind of broadband behavior. So we also, in our case, optimize some devices with different dimensions. So some devices show, resonant behavior, and some devices show this broadband behavior because of this canted angle. And when we connect this many devices of this dimension, then we see this broadband, kind of signal can be converted to low pass kind of rectification when we connect many broadband spin diodes. And when we connect this resonant one, then we can have this band pass kind of rectification, which we have already seen in the previous work, which I have shown in the, published in the Nature Com. So coming to the conclusion of this work, so basically we require the combination of series and parallel to control the impedance matching. So since we are using this wireless power, so wireless power also requires some kind of impedance matching with the devices. And for that, actually, we require some kind of hybrid approach. So that will be more useful. But in any case, right now, we have to increase the output voltage of the devices so that we don't need the booster and we can directly convert this into something like 1 or 2 volt. Coming to further development, so we are also trying to make some kind of on-chip antennas, and also we are trying to do some impedance matching for, realizing this kind of spin diodes for the actual applications. And so we have already achieved the low power operation of -62 dBm using this kind of match antenna. So this is very useful for the actual application from the Wi-Fi router. So coming to my second work, which is about the nonlinear Hall effect. So first I will introduce some words, for the general audience. So basically we have linear versus nonlinear kind of resistance. So in like crystalline silicon, we have typically this Ohm's law, V is equal to IR. But in some kind of WT2, typically where this inversion symmetry is broken, you have this linear as well as this nonlinear kind of resistance. So when we so what is the application of this kind of nonlinear transport where you have this nonlinear resistance? So basically, if you have this nonlinear resistance, I expand into your Taylor expansion, and you calculate the voltage, basically the Hall voltage from this nonlinear Hall devices. So you will have this equation, and by solving this, you will have this. These parts basically each part shows like linear term rectification and nonlinear second harmonic generation. And these two terms, which is one is the DC term and the second harmonic, is very useful for the applications. So what kind of system shows this kind of behavior, this nonlinear Hall effect? So there are three typical systems which are actually non-center symmetric. Basically, they break the inversion symmetry. So these are like topological insulator, Ashwa 2-3G, gas insulators, and these wild semi-metals, which are low symmetric crystals. So in all these, actually, we have observed some kind of very good spin orbit coupling, and they also show some kind of, the inversion symmetry breaking, which is very useful for the rectification and second harmonic generation, and for, of course, the nonlinear Hall effect. So the important question actually, so we use wire semimetal topological insulator where we have this strong spin orbit coupling, and with the inversion symmetry breaking actually, we have this topological material where we have this direct pines or wire nodes. So near these pines actually you can have this nonlinear Hall effect or second, harmonic signals. And these are very important for the applications. So the important question is actually how would the spin texture, which is very exotic in these devices, like in WT2, you observe some kind of spin momentum locking at the surfaces. So how this can be related with the transport property? So basically the rectification. So the next thing is, so we worked on some kind of materials where we have shown this Hall voltage can be generated in zero magnetic field. So for that, we have to first understand the Hall effect briefly. So in the typical electrical conductor, you have this ordinary Hall effect because of the presence of this magnetic field, which will break your time in reversal symmetry. So here also you have linear term between voltage and current. In case of anomalous Hall effect, again you have this magnetization because of this spin orbit interaction. You have this, this Hall effect where the voltage is generated at the sides. And in this case also you have this like linear behavior. So both are actually linear cases, but there are some materials where you can actually generate this Hall effect even without the magnetic field, without applying any magnetic field. And this comes under this nonlinear Hall effect. And that happens, there are some theories like Barry curvature and extension scattering, and typically the signature of this material, you have this dependence of, I square on versus V. So this occurs in typically like direct and wire materials. And since I showed you the equation, this is very important for the second harmonic generation as well as for the rectification. So this is again the equation which showed why this second harmonic generation and this nonlinear Hall effect is important for the applications. So recently this nonlinear Hall effect without magnetic fields because of the presence of this Barry curvature is actually shown by some theory and the experiment. But they have shown up to like 2 Kelvin to 100 Kelvin only. So this nonlinear Hall effect before our work actually was not seen at room temperature. So that was our motivation for going for this nonlinear Hall effect in some other materials. So we use this TIR-TE4 kind of wire semi-metals, and where we have seen this second harmonic dependence on the AC current. And so these devices having A axis and B axis, in one direction the inversion symmetric breaking, in the other direction is still there. So we observe this Hall effect only in one direction, which is your B axis basically in these devices. So which is shown in this, if we observe this Hall effect, the second order Hall effect only in this B axis, in the A axis we don't have anything. So finally, as our motivation was to observe some kind of nonlinear Hall effect in at room temperature also, so we have seen actually this from a various range from 2 Kelvin to 300 Kelvin, and it also changes sign with temperature. So we further, by some theory guys, it is shown that this happens, this change, this nonlinear effect, the change in sign happens because of this change in the chemical potential shift, which also changes your Fermi surfaces, your Barry curvature dipole, basically in these devices. Of course, this is a theory part, so I will not go into detail. So basically, because of this nonlinear Hall effect, when we shine a wireless energy on this, we observe a voltage, this rectified voltage in one direction only, which is the B axis, where your inversion symmetry is breaking in this TIR-TE4 wire semi-metals. In the other direction, we don't have any voltage. So that is a clear sign that this voltage is because of the nonlinear Hall effect. And finally, we have tried many devices like WT2, MOT2, platinum. So there we have not observed any kind of, nonlinear Hall effect. So that signifies that unless you have this inversion broken materials, you don't see, any kind of, this rectified voltage. And finally, coming to for the application part, of course, we don't require a single device because single device show only something like few microvolt only. So we have to make an array kind of structures to connect these many whole devices. And also there are some recent reports and some researchers are working on ferromagnetic materials by using the bilayers, because ferromagnetic materials can show a very high frequency signal. So basically they are looking if we can convert that resonance to rectify signal or not. Finally, coming to my future work, which is kind of developing some very high frequency kind of rectifiers, and for in that direction, I'm already working on some like ferrimagnets or some topological materials, and my motivation is to develop something more than 50 gigahertz. And for that, actually, of course, there's some problems with the current semiconductor diodes. Like there's a so-called terahertz gap between this 100 gigahertz to this 10 terahertz, where there's a gap between electrical diodes and photodiodes. So we don't have electrical diodes in this range. So there are some problem with the current semiconductor diodes like thermal threshold, limited transit time, low frequencies, which can be overcome by, this topological materials. Because of this band overlapping, they can show a very wide band, kind of rectification. And also this ferromagnet can be used for very strong resonant, kind of rectification. So, but of course, for the electrical measurement, we have to use this kind of very sensitive probe stations and very sensitive this kind of, VNA systems for the measurement. So finally, I'm thankful to Professor Murli and all other Spin Dynamics group members for all the support and the knowledge transferred to me. And I wish all the success to Spin Dynamics group at IIT Delhi. So thank you.
Okay, Raghav, thank you for this very interesting talk. So are there any questions? Maybe I can start one question. So when you were showing this different material where you saw the nonlinear Hall effect,
Yes,
you are showing the same 2.4 gigahertz, no? But I thought that you get this nonlinear Hall effect at twice omega.
Yes, sir. So basically, typically we perform this transport measurement in the PPMS, and there we cannot increase the frequency above megahertz, to demonstrate this second harmonic. But during the wireless signal, we only use single frequency. So we haven't seen, this kind of second harmonic. Maybe that's weak, but we are working on that.
Okay. So I thought the nonlinear Hall effect only appears in the second harmonic, or I'm not. Am I correct or not?
Yeah, it's correct. It's correct.
Okay.
So I have one question.
Yes, Akash.
Yeah. So you show this spin rectification using a series and parallel magnetization junctions, and there is a dependence with the applied or the Wi-Fi power. So do you have any specific reason that why it works really good around negative 30 dBm?
Okay, so basically this is we observe in our simulation also. So when we apply very high power, RF power to these spin diodes, so typically when we apply RF power, their precision angle increases basically. But when we increase a lot of power, actually the precision angle is not increasing in that, in that ratio. So basically when we keep increasing the RF power, so their sensitivity, of course, voltage will go up, but it's not in that ratio. So their sensitivity will go down basically. And of course, above certain power, they cannot work and your MTJ will break down.
Because of high current.
Yes. Okay. And of course, when we actually, this canted angle is very important. When we have a certain canted angle, something like 45 degrees, actually you require a very low power to excite this.
And what was the TMR in these devices?
Typically 70 to 80%.
And does it matter?
Yeah, it matters. Of course, the voltage is directly proportional to TMR.
So when you had this canted polarization or canted magnetization, did you observe these were orthogonal MTJs, right? Or
orthogonal means
they were completely in plane. Neither they were completely in plane nor they were completely out of plane.
Yeah, of course they were canted. So neither in plane, neither out of plane. So they were certain. At certain angle.
So I'm just wondering because in the orthogonal MTJs we usually do not observe any sharp magnetoresistance change. They usually have a very varying magnetoresistance, right?
Right.
Does it have any influence on the power, or maybe not? Yeah,
It
we
has
can discuss that
actually.
later.
Yeah,
Okay,
so
can you explain?
yeah, it has. So when you vary the scanted angle also, so you observe this very strong resonant signal and very broadband kind of. If it is broadband, actually, of course, the voltage and power will go down. If it is very resonant, of course, your amplitude will go up. So it basically depends on your optimization.
Okay, that's good to know. Thank you very much.
Okay. Himanshu Fulara, you have a question?
Yeah. So, hi Raghav, it's a nice talk. So I have one question. I'm just wondering, the frequency of the auto oscillation basically decides this rectification sensitivity or not? I mean, the rectification voltage you have observed, does
Yes.
it depend on the frequency of the auto oscillation or?
Yeah, of course. I mean, in the resonant case, of course, it's kind of similar what we observe in the auto oscillation. It's kind of similar frequency. But once you have this kind of very candid kind of amplitudes I have shown there, you don't have, I mean, this auto oscillations because your system cannot be excited at, I mean, one frequency typically. And then you observe this kind of very broadband kind of behavior where you can see many frequencies because you have this precession angle from in plane to out of plane. And it can cover many frequencies. But in the resonant spin diode, of course.
Well, I'm asking this question because in a simple non-magnetic paramagnetic bilayer also you can have this spin wave rectification effect, right?
Right.
So how does it different than this? I mean, because if it does not depend on the frequency, then we can have the similar spin wave rectification effect in a unpatterned film also.
No. Of course, it depends on the frequency. I mean, in the resonant case, of course, frequency is near to the auto oscillation. I mean, basically the FMR frequency of the material. And for the other part, the signal is very good in spin diode, not in the other devices because of the MR. So it's directly proportional to your MR basically. So since I have shown, I mean, because this is a multiplication of your I into delta R, so that delta is basically coming from TMR.
Okay, good. Thank you.
Professor Vincent, I have one question.
Yes, sorry, maybe I miss it. In the first part, you say that you have to achieve a kind of optimized impedance mismatch when you put several of these oscillators for the rectification, and you have to combine parallel and series connection, right?
Right.
Well, I wonder what is the best performance, the optimization. What is it in terms of number of parallel connection compared to series connection, for example? Do you find any optimum?
So till now, actually, the hybrid connections are not working in a way we want. Typically, right now we are doing this impedance matching with only series one. I mean, up to like 10 devices or a single device basically. But with hybrid, there are problem of like even, I mean, increase in capacitance and inductance, and that's very, I mean, problematic right now. So right now we don't have any good results about this hybrid approach.
Okay. So any other question? If not, I think we'll end this session.